Hello everyone, welcome to our webinar today. My name is Justin D'Souza. I'm a quantitative specialist and statistician here at Statistics Solutions. Today we will be covering a breakdown of regression models. So we will be covering 3 of the core regression models. If you have any questions during the webinar today, please type them into the chat box. I have a colleague, Melissa, who will be assisting with questions today. And I'll go through the entire presentation. And if we have any questions at the end, I will open up the panel to additional questions at that point. So today I will start out with a breakdown of the services that Statistics Solutions provides. We will cover the regression types. I will present a demonstration of our Intellectus software, and we will conclude with a summary. Statistics Solutions provides assistance with nearly every portion of the dissertation process. So no matter where you are in the process, if you're at the very beginning, at the topic development stage or prospectus, we can help you develop your topic. The way our company works is we will assign a methodologist to you, depending on if you're doing a quantitative or qualitative study. We will assign a specific methodologist to you, and we will assign a literature review specialist. So depending on where you need the most assistance, you may receive one specialist. If you need only help in one chapter, if you need help in multiple sections of the chapters, then we will provide multiple specialists to you. So we help all the way through the proposal, introduction, literature review, in terms of identifying articles. We assist with the methodology chapter and data analysis plans. So figuring out how to phrase your research questions, determining what type of design you're using, calculating your minimum sample size requirement, and what are the specific plans to crunch your numbers. We help with IRB forms, data entry templates. We have our own SurveyMonkey account, so we can help host your survey for you if you're doing an online survey. We assist with both quantitative and qualitative results chapters. We help with the discussion chapter, PowerPoints for defense, and journal publications. So if you've hit a roadblock as you're working on your dissertation and you need some assistance, you need some guidance to help expedite the process, please give us a call at 727-442-4290. Today's topic, we will be covering the 3 most often used regression models used in research today. Now, underneath each of these are subsets of regressions. I will touch on those, but we'll be focusing more from a general standpoint. So a regression is a statistical analysis or tool that tests the relationship between a predictor variable and a criterion variable. Now, when you see predictor and criterion, maybe you're not as familiar with that terminology. You might see independent and dependent variables. They're synonymous, they mean the same thing. But when you're dealing with regressions, typically predictor and criterion are the terminology that are used. A linear regression tests the relationship between a predictor and a continuous criterion variable. Continuous meaning interval or ratio. A binary or multinomial logistic regression tests the relationship between a predictor and a nominal or categorical criterion variable. And an ordinal logistic regression tests the relationship between a predictor and an ordinal criterion variable. So the choice on which regression you are going to run is 100% dependent on how your criterion variable is measured. The level of measurement dictates what type of regression you're going to run. So on the next slide, we'll kind of discuss what continuous, nominal, and ordinal mean. So here I talk about the predictors. The predictors in a regression model can be any level of measurement. It's the same type of measurements I mentioned for the criterion variable. You can have continuous, nominal, or ordinal independent variables or predictors. A continuous variable is a variable that falls on a continuum or a scale or an interval. Some examples of this include test scores, temperature, weight, BMI, height. The most common type of continuous variable used today is a composite score. When you use a previously validated instrument, for instance, the job satisfaction survey, the MLQ to measure leadership, when you combine a group of survey items together that are measured on a Likert scale, that new variable becomes continuous. So if you take an average of a series of Likert scale items, or you take a sum of a series of Likert scale items, that resulting variable is now continuous. And that would be a time to use a linear regression. A nominal variable is a variable that has two or more categories. However, these categories do not have an intrinsic order. Some examples of this include gender, ethnicity, passing or failing of an exam. So going to the previous slide, we talked about the binary or multinomial logistic regression. A binary logistic regression is used when you have an outcome that has two possibilities, such as passing or failing of an exam. A multinomial logistic regression is used when you have three or more possibilities for your outcome. For instance, if you're trying to see if GPA predicts ethnicity, then ethnicity is a categorical variable that can have three or more possibilities. For instance, white, Hispanic, Black, Asian. When you have three or more groups, then you use a multinomial logistic regression. Ordinal variables are variables that have two or more categories, just like a nominal variable. However, these categories can be ranked or ordered. A good example of this would be education. Education, really an ordinal variable is a subset of a nominal variable. It's categorical, however, there's an order to it. If you give a multiple choice questionnaire to measure education, you might see it start out with less, less than high school, bachelor's, master's, PhD, and so forth. It goes up a ladder. When you see a variable like that, it is ordinal. Another ordinal type of question would be a Likert scale survey. If you're using one question on a Likert scale, that is an ordinal variable. An example here, the most common that we see today would be strongly agree, neutral, disagree, strongly disagree, something like that. This is a 5-point Likert scale. You might see 7-point or even 9-point. Those are all ordinal variables. For the coding of your independent variables, no adjustments need to be made for continuous data. So if you have a predictor variable such as a test score, weight, BMI, temperature, you just enter that variable into the model as a predictor as it is coded. You don't make any adjustments. If you're using a dichotomous predictor, such as passing and failing of an exam, the most common procedure is to code the absence of the condition as a 0 and the presence of the condition as a 1. For example, when passing and failing an exam, it's easier to interpret your regression results if you code 0 as a fail and a 1 as a pass. So always put the absence of the condition as your lower value. If using a nominal variable with 3 or more groups, or using an ordinal variable, typically you're going to need to dummy code your predictor variables. Now, dummy coding is a procedure used when you have a categorical variable with 3 or more groups. In our previous example, we just had 2. We have a nominal variable here for passing and failing an exam. There are only 2 possibilities there, so you don't need to follow this dummy coding procedure. But once you introduce another group and you have 3 or more, you have to use this dummy coding procedure. The reason is that a regression analysis cannot differentiate what these categories mean. It can't understand what categories such as white, black, Asian, Hispanic, it has no concept of understanding what that means. So it's our job to assign meaning to those categories. And the way we do that is by assigning a reference group. So typically what you'll do is you'll run descriptives or frequencies and percentages on your demographic question or on your categorical question that needs to be dummy coded. And whatever response has the most frequency or the highest response, that is going to be your reference group. So in the example of using ethnicity, if after giving your questionnaire, you see that the white response was the highest, you're going to assign white as the reference group. And you're going to create 4 dummy coded variables. You would have black versus white, Asian versus white, Hispanic versus white, and other versus white. What is going to happen is you'll have 1 less number of variables than the number of categories. So we had 5 possibilities for ethnicity. We now have 4 dummy coded ethnicity variables, all coming back to our reference group of white. Now, it would take me an hour to fully explain this process and how to code your data appropriately, but this is a very common procedure. If you just go on YouTube and check out dummy coding for a regression, you'll see videos that explain the entire process and discuss how to code the variables appropriately. You can even just Google, if you go on Google, maybe check statistics layered, they will describe the procedure of dummy coding. Once you have coded your variables, you've inputted the model into a regression, you first need to verify that the statistical assumptions of these analyses are met. Now, linear regressions have more stringent assumptions to verify in comparison to logistic regressions. Linear has, because you have a continuous dependent variable or criterion variable, you have to check the parametric assumptions for this, as opposed to a binary logistic regression or a multinomial or ordinal logistic regression. When you do a linear regression, you typically check these 3 assumptions. Depending on what reference you read, they may list more assumptions. These are the most common procedures I see. So you need to verify that your data follows a normal distribution. So you check for normality, which is typically done with a normal PP plot or a normal QQ plot. You then check for homoscedasticity with a scatter plot of residuals. And ideally in the scatter plot, you want to see the absence of a pattern. You're making sure that the residuals are randomly distributed, meaning that there's no relationship or each participant is independent of one another. Then if you have multiple predictors, you want to check for absence of multicollinearity. Multicollinearity is verifying that your predictor variables are not too closely associated with one another. You don't want a high correlation between your predictor variables. So for instance, if you're using the MLQ leadership questionnaire, which measures transformational, transactional, and laissez-faire leadership, and you're putting all of those into a regression to predict job satisfaction, ideally you don't want your 3 leadership styles to be closely associated with one another. You want them to be fairly independent. There are many ways to check for absence of multicollinearity. One way is to run a correlation matrix, a Pearson correlation matrix or a Spearman correlation matrix, and ideally the correlations should not be too high. Depending on what reference you read, you might see a cutoff correlation coefficient of 0.9. Some textbooks say 0.8. You kind of want to play it by ear, I would say. Depending on what the findings show, if it's above 0.8, I would say that's reason for concern. But I have seen some textbooks say 0.9 being the threshold. So just double check that. Ideally, those values are not too high. Another way to check for multicollinearity is through variance inflation factors, or VIFs, they're sometimes called. And ideally, those values are also low. Below 10 is the threshold typically for VIF values, indicating that you don't have a high correlation between your predictors. Once you've checked for assumptions, you then want to run your regression model and interpret. Now, it seems like it's daunting at first. Where do I begin interpreting the regression? This looks like a different language to me. There are so many different symbols, and what do I do? It's pretty straightforward. If you just follow this process here, there are 3 steps to interpreting regressions. First, you want to interpret the omnibus test. When you run a linear regression, it's going to present an F-test. When you run a logistic regression, it's going to present a chi-square test. You want to interpret the p-value of those omnibus tests first, and you want to look for a p-value. The p-value tells you whether you have a significant regression model or not. You want to make sure that the p-value is less than 0.05. If the p-value is less than 0.05, then you have a significant regression model, significant collective regression model, I should say. Collective being the key word here. That's what the omnibus test is checking. Then you want to interpret your coefficient of determination. The coefficient of determination is designated with the R² value. When you do a linear regression, it's called a R² value. When you do a logistic regression, it's called a McFadden's R². An alternative might be called a Nagelkerke R². You'll see that in SPSS. Every time you run a regression model, you want to check step 1 and step 2. No matter what, you always run step 1 and step 2. Step 3 is run contingent on if step 1 is significant. So if you have a significant omnibus test, then you examine step 3. And step 3 is examining each predictor in the model on its own. If you don't have a significant omnibus test, a significant F test, or a significant chi-square test, then you stop right there and you say, our collective model was not statistically significant. We are not going to interpret our predictors on their own. However, if step 1 is significant, then you do interpret each predictor on its own in step 3 here. And you do that with interpretation of a t-test for a linear regression, or a walled test. Sometimes that's a chi-square test, interchangeable, for a logistic regression. If you have a significant predictor variable, meaning that the p-value for the predictor is less than 0.05, then you want to interpret the beta coefficients. For a linear regression, you interpret the unstandardized beta coefficient. which is usually a Greek symbol beta. For a logistic regression, you interpret the odds ratio. So at this point, I'm going to provide a demo for Untitled Statistics, which is our company software for analysis. This is what our company software looks like. And the first step you can do is upload a project. So you'll see here, we can upload a project. I'll just call it webinar for December, example. We have 3 options for uploading files. You can upload a file in multiple formats. If you have a URL for your data, you can upload it that way. You can also enter your data in manually, kind of like an Excel file or SPSS. If you have a file, we have 5 different formats: CSV, Excel, SAV, which is SPSS, SAS, and Stata, so multiple softwares. I will show you some examples of linear regressions today. But before I get there, I do want to touch on the methodology process. Before you even upload data, we have a priori information here, starting with the decision tree. So if you're at the very beginning of the process, maybe at topic development, or you've just started your methodology, if you have research questions, but you don't know what analysis to run, the decision tree is a useful tool for figuring out what analysis should I use to crunch my numbers. So say for today's topic, at the top here, we're trying to predict an outcome. That is going to start you down this path. And it's going to lead to a type of regression, but we don't know which one yet. We have to give more information. Do we have a scale, nominal, or ordinal dependent variable? Say we have a scale variable. You can see how the decision tree goes down the path and indicates what type of regression needs to be conducted. So as we discussed, the regression is 100% contingent on the outcome variable and how it's measured. So if we have a scale variable, we need a linear regression. If we have a nominal variable with specifically 2 levels, kind of like pass fail, it would be binary logistic. If there are more than 2 levels, multinomial logistic. We have an ordinal dependent variable like education, then we do an ordinal logistic regression. Once you know your analysis, you can go to data analysis plans here. And this is typically a section in the methodology chapter. At most universities, you need to indicate how you're going to analyze your data from step 1 all the way to step 10. What are all the different steps you're going to do in between? So for today's topic, we discussed the regressions. So we have 5 different types here. In Intellectus, we have a linear regression, logistic. Linear and logistic are really the 2, but then we have subsets. So there are more specific types within each of those. Say we select a linear regression. What Untitled Statistics is going to do is it's going to provide a sample write-up for what needs to go in your methodology chapter. It's going to give you sample research questions. So does independent variable 1, 2, and 3 significantly predict your outcome or dependent variable? It then provides null and alternative hypotheses. And it gives a breakdown for the entire regression. What assumptions should be checked? What is the process for interpretation of the regression? It also provides references at the bottom, peer-reviewed references. So this is a very useful tool for just filling in the blanks of what needs to be inputted into my methodology chapter. We also have a power analysis section here that can help you determine what is the minimum sample size requirement for the analysis that you're running. To keep it consistent, we'll stick with regressions today. We have a linear regression, and Depending on how many predictors you have in your regression model, the sample size changes for a power analysis. At the top left here, you can see we have one predictor entered in right now, and we give 3 sample size write-ups depending on the effect size you're planning to use for your regression. If you have a large effect size, you can see the sample size requirement right here, 25. If you have a medium effect size, you need 55 participants. If you're using a small effect size, you need 395 participants. This power analysis write-up is based on G-Power software, which is right here. So G-Power is a tool used for generating the sample size calculation. So we've taken the results of G-Power and we've condensed it into write-ups here that tells you specifically what is the sample size you need to target. Typically, a medium effect size is used in studies for regressions, t-tests, ANOVAs, things like that. If you don't have literature to support using a specific effect size for your analysis, then use a medium effect size. If you do have specific literature that says we should be using a large effect size here, we are anticipating a strong relationship, then you would use a large effect size. On the opposite end of that, if you're anticipating a small relationship or a small effect, then use a small effect size. But in the social sciences and psychology fields and business, a medium effect size is most often used. So we can also change the number of predictors up here. Say we have 5 predictors in our model. Instead, we can see here that the sample size numbers have changed. The more predictors you have, the larger the sample size requirement. You can also run a power analysis for a binary logistic regression. In my experience, personally, I try to avoid this because the sample size requirement is always pretty high if you're doing a binary logistic regression, and it's not really contingent in this case on the number of predictors you have. I tend to use what we have here under the multinomial logistic regression write-up. I tend to use rule of thumbs, this section that I'm highlighting right here. We have a couple citations here that specify what is the minimum sample size to use for the number of predictor variables you have in your regression model. Hosmer and Lemichel here identify that you should aim for 10 to 20 observations per predictor variable. So if you have 5 predictor variables, using this reference, you should aim for 50 to 100 participants for your analysis. We also go with the more conservative citations here, if that's an option. If you anticipate, you can kind of cater it to your needs here. If you feel like you can obtain a large sample size, then go with a reference that supports needing more people. In this case, LeBlanc and Fitzgerald suggest a minimum of 30 observations. So if you had 5 predictors, you would need 105 and 30, 150. 150 participants in that case. So yeah, you can adjust, you can use the appropriate citation based on your need. During COVID now, obviously it's very tough to sample participants. I've seen a lot of struggles recently in terms of collecting an adequate sample, and that's okay, that happens. So when you write your methodology, you want to make the appropriate adjustments. You want to find a citation that supports using a smaller sample size for your study. And when it comes to your results and interpretation and the following discussion, if you don't obtain your minimum sample size, you want to interpret your results with a level of caution because the achieved power is reduced. So be cautious in interpretation. Okay, let's go through some regression examples here. So as I mentioned, you can upload a project. I have some examples here. Once you upload a project, this is what it looks like. It looks like SPSS. You can see the variable names. You can see all the coding that has been done on the spreadsheet. So this survey, this is just an example. It was used to measure well-being. So it measured 5 different dimensions of well-being, engagement, perseverance, optimism, connectedness, and happiness. On the left side here, we can see all the data management tools we have. You can edit your data. If you want to make adjustments, you can change a certain row, you can change a value. You can change the level of measurement, say something, instead of being scale, it needs to be nominal or ordinal. You can do that. We have converts to dates. You can recode multiple variables at once. If you have a survey question that is negatively phrased and you need to reverse code, we have an automatic tool here for that. We have imputation for replacing missing values in cells. We have removal of both univariate and multivariate outliers. We have a variable calculator here that can be used to create composite scores. And we also have transformations and binning. And once you've made any adjustments to your spreadsheet, you can download it right here into a CSV file, which can be opened in Excel. Going to analyses here. Today we are running regressions, and we do have many options for analyses. I'm kind of sticking with the topic today of examining regressions, but we do cover every key analysis that are used in dissertations today. If you need to check for assumptions, you need to run descriptives or present reliability with Cronbach's alpha. You have 5 different types of correlations. The most common you'll probably see are Pearson and Spearman. Z-tests, proportion tests, t-tests, several different types of ANOVAs. We have MANOVAs if you have multiple dependent variables. These are the regression methods that we have here. Non-parametric tests, which are used when you have non-parametric data or maybe non-normal data. Path modeling analyses. So these are some of the more advanced procedures here: path analysis, CFA, SEM, PLS, as well as mediation moderation, HLM, survival analysis, and time series. So the list is extensive for the analyses that you can run in here. Let's look at a linear regression here. What I'm going to run is to see how the subscales on this instrument, engagement, perseverance, optimism, and connectedness, those are going to be my predictor variables, and I want to see how these predict happiness. You can go to options at the top right here, and you can see specifically what assumptions are we going to verify. Typically, you want to check for normality. You want to check for homoscedasticity. Absence of multicollinearity will be done with variance inflation factors. We have many other options. Calculate, and the regressions run for me automatically. We have a full APA write-up. We have plots and charts that are in APA format, and we have interpretations. Okay, so the linear regression model starts with the verification of assumptions. First, normality is checked with a QQ scatter plot here. And if you hover over the graph, you can see what is ideal for the assumption to be met and what the assumption would look like if it's not met. As we hover over this one, we can see the data does appear to follow a normal distribution. Our data closely follows this diagonal trend line. Homoscedasticity is evaluated here with a residual scatter plot. And we can see if we hover over this graph, what the data needs to look like ideally. We want it to look like the #1 gradient here, where the data is randomly spread. That is the case here. Multicollinearity is checked with variance inflation factors, and we have a couple citations here to support that ideally these values need to be below 10. And that is the case, indicating that engagement, perseverance, optimism, and connectedness are not highly correlated. Then we get to our regression model, and it gives a full interpretation for the regression. So as we come down to the table here, the table, if you're not familiar with how to interpret a regression, the table here really summarizes everything. So we'll follow the steps that I outlined in the PowerPoint. Excuse me. We have 3 steps here. First, we want to interpret our omnibus test, then interpret the coefficient of determination. Then, if our omnibus is significant, interpret the individual predictor variables. The omnibus test is presented in the note at the bottom here. We have an F test, we have degrees of freedom, which tells you how many predictors you have. We have 4 predictors, 78 has to do with the sample size. And the most important part here is the p-value. The p-value in this case is significant, telling us that collectively, engagement, perseverance, optimism, and connectedness do have a predictive relationship on happiness. Our R-squared value is 0.74. If you move that decimal over right twice, that is 74%. The interpretation for this is that 74% of the variance or change in happiness can be explained by these 4 predictor variables. Because our step 1 was significant, our omnibus is significant, we can now go inside the table and interpret each predictor on its own. And we want to look at the p-values. We can see engagement has a p-value of 0.004. That is below the significant threshold of 0.05. So we do have a significant predictive relationship between engagement and happiness. Because this variable is significant, we now go to the second column here, our unstandardized beta, and this value is 0.22. So the interpretation for this is everything I've said has been discussed up here. So collectively, we have a significant regression model. That's what this shows, indicating the R-squared. This is interpreted here. 74% of the variance is explained by the predictors. Engagement is a significant predictor. So now the beta is interpreted for engagement, and that is discussed here. So with every 1 unit increase in engagement, happiness scores tend to increase by approximately 0.22 units. So we have a positive relationship between those 2 variables. Then we go to perseverance. We look at perseverance and we go to the final column here. Perseverance is not significant. This p-value is greater than 0.05. We do not interpret the beta for perseverance. We stop right there. We go to optimism and connectedness next. Both of these are significant, so we interpret our beta coefficients for both of those. As optimism increases by a point and as connectedness increases by a point, happiness increases by 0.64 units and 0.28 units, respectively. So it looks like there's a positive relationship between engagement, optimism, and connectedness. If one of these predictors was significant and had a negative beta coefficient, it would be an inverse relationship, meaning as one variable increases, the second decreases. That pretty much covers it for a linear regression. I'll show you a logistic regression here. So in this example, I'll show you the data set. This was a survey given, and it was a nursing exam, which is the NCLEX, and multiple subsets of the NCLEX were reported. One of the research questions on this was to examine how GPA, the overall GPA in nursing school, predicts passing and failing of the NCLEX exam. This would be a logistic regression, as we have passing and failing as our outcome. We go to analyses, we go to binary logistic regression, we'll select a dependent variable, NCLEX, passing and failing. And as we discussed in the PowerPoint, you want to make your reference typically the absence of the condition. So the lower number, the absence of passing, which in this case is failing, needs to be the lower response or the reference. The independent variable will be GPA. See how GPA predicts passing and failing. And for a logistic regression, there aren't many assumptions to check, as we discussed in the PowerPoint. Okay, so here we can see the logistic regression model, and we do have a significant relationship signified by the p-value down here. We go inside the table, and for a logistic regression, you interpret the odds ratio. You have a beta, but you interpret the odds ratio in this example, indicating in this example that the odds of experiencing a pass for the NCLEX increase by 350% based on a 1 unit increase in GPA. So as GPA increases by 1 unit or 1 point, the odds of passing the NCLEX increase by 350%. Sometimes you see it written as a percent. Sometimes you'll see researchers say, as GPA increases by 1 point, the odds of passing and failing, the odds of passing the exam are 4.5 times more likely. So this is really 4.5 times or 350%. Both are accurate. Okay, so those are some examples of regression models. Again, we do have lots of options here. We even have plots. So if you need to run a certain type of plot to prove your relationship, you can do that here. Just for an example, so we have plots here. You can then edit the plots however you want. And you can change the font sizes, the inputs, colors, if you want to take out the color and make it grayscale. Then you can add these to your analyses and then download the document. Lots of options there. We also offer consulting sessions for Intellectus. It's a great deal for $99 a month. For every day of the week, you could join us. 5 days a week, 4 weeks, you can join us, and we do one-on-one consulting with Intellectus. So you can come join us. We have a specialist there who will help you. We have up to 6 people who can join for each day, and they will answer any questions you have about the software. They will also help you determine the best analyses you can run. Given your research questions, what is the best analysis to address your research question? They can help you clean your data It can help you create composite scores and run your analyses and interpret appropriately. A great deal that we're doing right now. Check that out. Okay, so back to the PowerPoint. That pretty much covers our webinar for today. So in summary, if you're trying to predict an outcome variable, a regression is probably the best tool. Prediction is the key word here when you're looking at a regression. Then you want to determine the best regression method depending on the level of measurement for your criterion variable. If you have a continuous or interval variable, then you do a linear regression. If you have a nominal variable, you do a logistic regression. If it's dichotomous, that'll be a binary logistic. If it's multiple groups, like ethnicity, you do a multinomial. Ordinal, like education, then you do an ordinal logistic regression. Then you want to verify that your statistical assumptions are met. Remember that a linear regression has far more stringent assumptions to check in comparison to logistic regressions. Then you want to follow the 3 steps for interpreting a regression, starting with the omnibus test, interpreting your R-squared values. And if the first omnibus test was significant, then you interpret each predictor variable on its own. And then you can use intellectus statistics to analyze your data and present interpretations. So that covers our presentation for today. Just to reiterate that Statistics Solutions does provide assistance with every part of the dissertation process. We assign a specialist to you depending on where you are in the process. If you need help with the methodology, either quantitative or qualitative, we'll assign a specialist to you. And if you need help with the literature review or discussion, we'll assign a specialist to you for that, and we'll help expedite the process. So for a free 30-minute consultation, contact us at info@statisticsolutions.com or give us a call at 727-442-4290. I will now open up the panel for questions if we have any. You can type those into the chat box. Looks like Melissa has answered a few questions. If anyone has a question, please type it into the chat box. Yes, we do work with faculty, depending on where you need assistance. If you need a summary of assistance we can provide with dissertations, we can assist with that. We also help faculty with setting up the Intellectus software. So if you need to administer Intellectus to your students, that is something we provide as well. Yep, we assist with faculty, students, even if you're independent and trying to run your own project, you assist with that. Sounds great, Valerie. Look forward to hearing from you. Yeah, you're welcome. Do we have any additional questions? I can answer questions about the software, about Intellectus, about regression models, or the services we provide. You're welcome, Elizabeth. Thanks, Bernicia. Appreciate the feedback. Do we have any additional questions? I'll stay on for about 5 minutes. We will be sending everyone a copy of the webinar following the presentation. There will be a copy of the video recording as well as the PowerPoint itself. Thank you, Stephanie. Appreciate the feedback. Have a great day as well. We have any last questions? Hi, Elizabeth. Elizabeth's question is, for a project that is already completed, what if we want to use your services to make sure everything was done and interpreted correctly? Great question. Yeah, we absolutely can run your data again. If you're at the results chapter, we can run the data again and verify that the analyses are presented correctly and that the interpretation is accurate. That is absolutely something we can do. You're welcome. Okay, I'll stay on for a couple more minutes. Any additional questions? All right, thank you for joining us, everyone. I'm going to head out. If you have any questions, please contact us again at info@statisticsolutions.com or give us a call at 727-442-4290. We do additional webinars like this. We do 8 of these a month. We have 3 other specialists who focus on different topics, so I do the quantitative ones. We also have a specialist who does qualitative projects, so qualitative methodologies and results interpretation, and we have a literature review specialist who can help you with the theoretical framework, selecting articles, and the literature review process. So check out those webinars as well. As always, stay safe and have a great holiday. Take care.